Hi everyone. So for today, I'm going to record this Make More Part 1, which is from this video. And basically, in this tutorial, Andrew Capsi built a migrant character level language model. And he built it in two ways. The first way is like we use statistical model to predict what is the next word if we have given a character. And the second way is that we build a simple neural net to predict. And you will see that these two ways will end up with the same result. Yep. And so let's just get into the code. So first we have this names.txt, which is like the names like Emma, Olivia, Ava, something like that. And we have 32,000 of them. And we want to build that bytecode, which is like there are two characters, which means that, for example, here this A and means that the N is followed by A, and we want to count like how many times it occurred in our names list. So we just create a dictionary, and for because we also want to know that what character may be the start or end. So we add a start symbol here, and we append it by the list of words, and then append it by end. So it means that for every word, for example, A, B, yeah, it will become like S, start A, B, end, B, end. Because we do this operation here, and we already told in last video. So now we have this pipeline here, and we just count them, and this get means that if there is in dictionary key pipeline, we just get the result. Otherwise, we return zero, and then we add them. And now we have the sorted the eight items of the dictionary, which returns a tuple of the key value pairs. And now we use the second element, which is the frequency, like the count, how many times it happened. And because we want to order it from big to small, we use this negative here. So now you can see that we have the diagram here. Like for example, for EN, this happens in all of the names 2,675 times, such like that. Okay, so now we want to put it in a table to see, like to visualization it. And look here that we use this dot to replace the start and end, which means that the start is this dot and the end is also this dot. And we create this S2I array to make the change, the like translation that for dot is 0 and for A is 1 and B is 2 blah blah blah. For Z is 26 and I to S is just the reverse of S2I. So basically here is the same as like we just covered. And we put the our count into this n table, which is torch zeros, 27 by 27, because we don't have start and end symbol, we only have this dot symbol here. And so now we draw this image here. You can see that, for example, here. Okay, this one DE. So it means that DE, this pattern happened in all of the names, 1,283 times. Okay, so now we want to know the probability of if we have a character, what's the probability of each character will occur. So we need a probability distribution, which we calculate by P here. Like we take this the first row, which means that if we are given a start symbol, what will the probability of the next character? And you can see that the answer is here. Yeah, and this zero means that start followed by start is zero, of course. And start followed start A, and start B, start C. Yeah. And here we use this torch type polynomial to sample. You can see that we have this probability, a sample one times. Replacement true means that when I sample, I will put the result back into the multinomial, means that the probability won't change. And we use this generator to make sure the seed that to set the seed, which makes our every time we test every time we'll have same result. And we use this item to get the integer inside this uh, torch object. And we use I to S you can see that the result is N. And what does this symbol means? For example, if we have this probability, like for 0 is 60%, 1 is 30%, 2 is 10%. If we sample 100 times, we can see that here the result, like there will roughly be 60% of 0, 30% of 1, and 10% of 2. Okay. So now how can we do this? Like we only do this for one row. Like we want to do for all of the row. Means that for all of the character, we want to know that what are the probabilities of the next character will be. So now we run this. Okay, so what does this mean? Actually you can see here. This means that for each p, we divided its sum, which is squeezed from the not first, the index one dimension, which is the row dimension. For example, we have this 27 by 27, which is this p, and we squeeze the 227 by 1. Means that the sum is like we sum all of the row. Yeah, and here you need to here's the point that you need to keep the dimension be true because of the brackets rule of PyTorch. If you didn't keep this dimension when you want to do this operation here, you will end up be like this. Like it's 127, but you really want is 27.1. Because you want 27.1 and it to copy to all of the row element. And then each element is divided by the sum of that row. If you didn't keep dimension, it will be like divided by the sum of the column, which is not right. And here this plus one is because that sometimes we don't want uh, our probability to be zero. For example, here, let me see. Here, okay. You can see that if we put this, because JQ here doesn't happen in the table, so because we add one, so here you can see that we can still count the negative log likelihood. Yeah, we will cover that later. But if we didn't do this plus one here, if we didn't do this plus one here, it turns out like our loss function is infinity. And if our loss function is infinity, which means that we cannot make it like this is what not the result we want. Like for example, maybe our original data set doesn't cover this type, and we don't want to be overfit the original data set. So this is a kind of it's called like add one smoothing, like it's a technique that to make sure that your model can perform uh, something that you didn't think in your data set. Yeah. Okay. Let's go back to the code here. So here our goal is to maximize the likelihood of the data with respect to the model parameters. And it's equivalent to maximizing the log likelihood because log is monotonic. And it's equivalent to minimizing the negative log likelihood. And it's also equivalent to minimizing the average negative log likelihood. So you can think that all of these steps are just like uh, make us easy to calculate the metric. Okay, so now how do we calculate our metric here? This negative log likelihood. We just like go through this, and you can see that we have the probability which we sampled, and we run to our log, and we accumulate our likelihood, and this is the average negative log likelihood here, which is 2.47. And yeah, okay, and I think this covers the statistical model, and which we will use the neural network, like we will have a random W here, and after training, you will find like this W will be very, very similar to this probability table we will have. Yeah. Okay. Okay, so let's go to the second part. Okay, so now we have this excess and y, which means that if we want to input 0, output 5, input 5, output 13, which means that when we input this dot, we want it to E. And if we input E, we want it to output M. Yeah, because we only uh, originally said now it only has the first word, which is M. And we use this one hot encoding to represent that for this 27 by 1 by 27 array. Means this 0 here because it's index. And for 5, we just set index 5 by 1. So this is a way to to transfer our scalar into a like vector, like, which is called one-hot encoding. Okay, so we want to put this 5 vector into the model. And actually, normally we can just use this 27 by 1, and our output will be 5 by 1, because 5 by 27 uh, times 27 by 1 for the matrix multiplication will just output 5 by 1. But we want output is a probability that for any input, what is the probability of the output of each token's output. So now with the set W becomes 27 by 27 here. Yep. And so for here, like is okay, we use this W to be 27 by 1, and like we will have this probability 0 here. This means that if the first input is 0, what will be the second? Like when we assign some is higher here. Actually, we cannot say anything because this W is like just a random, and we only just for one pass, so this doesn't mean anything. Yeah, we want this to be like the ideal because we enter 0, so output 5. So ideally, we want this 5 be 1 and the other be 0. Yeah. Okay. So because we want output to be a probability means that it has to be like 27 here. So we just do the same thing here. Like we set a seed and use this random 27 by 27 and one hot encoding R X. And we calculate the log counts. We predict the log counts, and then we do exponential, and then do to transfer it to the probability, and which is two lines is called softmax. And now we have this cross shape, 5/27. And how can we sample by the probability? Yeah, we can just run this. And you can see here. So for this dot E, we input 0 in here. And this is our output. 0, 1, 2, 3, 4, 5. Yeah, because it's only this W is not training, so we can see that the correct character probability is this 5 here. And we calculate the log likelihood and negative log likelihood here. And after that, we can have this average negative log likelihood, which is our result. And we want this result to be as lower as possible. We want to minimize the negative log likelihood, which means that we minimize the loss. Okay, so now we can do some optimization here. Like now we put all of the operations we make about it's called forward pass. And you can see that this this likelihood is still the loss is still same, right? It's not the same, but like just the operation here is the same as what you do here. Okay. And now we add the backward pass. And in whitewash, you can just set the grad to none, which means 0 in whitewash. And we just run last step backward. And because whitewash has like similar structure, tree structure as micrograph we built before, so it will propagate the backward function, and you just need to run at the loss backward, and all of the nodes can build loss will also run their backward function. And then we can do update, like we just update as what we do in micrograd. Update by this is the learning rate 0.1 and the gradient. Because gradient means that how much increase will increase the loss. So we want to make loss smaller, so we just times a negative number here. And okay, so I think all of this below this code are actually same. Yeah, because and here the code also shows the number of examples here, and this is all same and backward update, and we change the learning rate to be a lot bigger. And this you can decide that how many times you want to do this gradient descent. Gradient descent means actually forward, backward, and update. Okay. So the last step is we want to sample from this neural net model. Before we simulate, we just use this table, probability table to sample. But now we use this probability comes from the neural net, and it's still the same sample result. And you can see that the result is identical as the probability. Yeah. So in this code, in this experiment, now we found that we can train our best result gives from the neural net is will be like the same as the probability table. Yeah. So why we still want to be neural net? We use neural net because neural net is more flexible than the table. For example, if we want to predict for the next step, we will need to predict like we have a lot some not just the previous character, we have previous characters and predict next character. So if you want to put all of that information into the table, is impossible. So we need another way like to calculate the probability and to sample from it. Yeah, and that's why neural net is more flexible because we can use more complex uh, neural net structure to solve the more complex questions. Yeah. I think that's all for today.